Okay, so don't worry about it. You're here. You're not going to get to see that one. All right, so our last speaker is Melodie Yashar, and she is going to talk about the Mars Ice House, designing for human factors in space exploration architectures. And yeah, here you go.
Thank you.
I'll give you a full 25 minutes for
Sure. My name is, can you hear me all right? Yes. Okay, great. My name is Melodie Yashar. I'm here on behalf of Search Plus, which is short for Space Exploration Architecture. We are an organization of primarily architects, but also industrial designers, creative technologists, roboticists, and we're based out of New York. 2 years ago, we collaborated with another group called Clouds AO, and we won first place in NASA's Centennial Challenge for a 3D printed habitat on Mars. So this is a presentation. It's usually a much more extended talk, so I'll move quickly. But it's a presentation that runs through that proposal, that winning proposal for Mars Ice House. Myself, as well as my colleague Michael Morris, as well as Rebecca Pellis-Friedman, teach at Pratt Institute, and right now we are in the third year of the XHAB Academic Innovation Challenge put out by NASA to basically collaborate with university partners in creating proposals for Martian habitats, surface habitats, as well as transit habitats. So that's a little bit of my background, and I will jump right into the project. So this is the structure of our presentation, my presentation. We'll start very, very broadly with the landscape of space architecture today and run through a couple of projects that many of you, I'm sure, are familiar with. And then we'll go into a bit more detail about the proposal itself. So space exploration and Martian architectures. I think it's clear, particularly in the company of this audience, that we are underway to becoming a spacefaring civilization. And naturally, the examples of space habitats and space architecture have existed in popular culture for several decades. So now that we find ourselves in a time where space tourism and commercial space flight are just about to become a reality, it seems clear that Martian habitats and the sustenance of life on the Martian surface are going to become a true necessity of future missions to Mars. So as we see that there are already many ideas and concepts, speculative and theoretical, for what Martian life is going to be, what Martian architecture is going to be. And so we really see our work and our project in this case as working within this lineage of existing projects, of existing ideas of what space architecture is, but with one crucial difference. Being architects, we have a very profound interest in human factors engineering. So our mission is not only to propose a systems architecture for astronauts to survive on the red planet, but also to thrive, for them to have a prolonged sense of psychological and physiological well-being. So those are our research interests. And in a moment, this is our proposal. It's called Mars Ice House. And what it is a proposal for using indigenously mined water ice to 3D print a habitat on Mars in the northern hemisphere. So the competition, as I mentioned earlier, was based off of, we created this proposal for NASA's Centennial Challenge for a 3D printed habitat, and the judging criteria and the requirements you can see here. They were looking for a proposal for a crew of 4 to be living and working on the Martian surface for 1 Earth year, and they gave us very specific program and functional requirements that would be integrated. And so this is our team at NASA Langley, as well as at the awards ceremony at the Maker Faire in New York. And as I mentioned earlier, our team is comprised of Search, which is myself, Christina Trardula, Michael Morris, Kelsey Lentz, Jeffrey Montez, and Rebecca Pellis-Friedman, as well as Clouds AO. And we collaborated with about 18 research consultants ranging from planetary geology to robotics to astrophysics, and it goes on from there. So Mars, the extreme frontier, many of you are going to be familiar with the environmental factors that are involved in proposing and creating a surface habitat, but I think it's useful to run through this because myself, being a terrestrial architect in addition to a space architect, it really hits home once you start designing what the differences are, what the significant differences are between an Earth-based habitat and a Mars-based habitat. So of course, site and terrain. There are landing site considerations to take into consideration when designing and selecting a site for a Martian habitat. And in particular, we were very concerned with the danger of perchlorates and the toxicity of Martian regolith. So this was a big red flag for us because a majority of Martian proposals for human habitats bury the habitat underground for the sake of radiation protection. But we were concerned about the use of, about the danger of perchlorates, and we're wondering how we might work against that. Gravity, of course, Mars is only is 38% of Earth's gravity. Atmospheric pressure. Temperature, of course, there's a massive temperature differential between day and night on Mars. Wind, despite the fact that it's a low pressure environment, dust storms from the regolith can last for months. And then of course radiation, which is the biggest factor and really the thesis of this project in providing a habitat that will protect humans and prolong life for years to come. So where do we start? Our goal was to design a habitat that is self-sustaining, autonomously deployed or semi-autonomously deployed prior to humans' arrival, and scalable in design. So we proposed a habitat made of water ice. Why water? We imagine that for a prolonged Martian mission, there's going to be water mining and water excavation happening anyway for the sustenance of life. So we saw this as a natural extension of that process. So water is a source of life. It's an effective radiation shield. In the research that we conducted, we discovered that it's even more radiation protective than aluminum as well as regolith, Martian soil. It'll provide natural light for humans and plants. It'll provide translucency to an exterior landscape of the Martian vista. And we find this is incredibly important for human health and psychological stability. So again, a vista onto the Martian landscape doesn't really seem like it would be all that important, particularly when related to human health and the sustenance of life and the dangers of radiation protection. But why would you travel all that way just to be buried underground, and not really sense or have an understanding of the magnitude of the journey that you're on, of the mission that you're on? We really feel that a connection to the Martian landscape is really going to send that idea home for the astronauts. And we think that as a first outpost on the red planet, it's incredibly powerful and incredibly important. So again, radiation protection. As I said, we discovered that water, compared with aluminum and regolith, has superior radiation protection qualities. So that was a big impulse for us to use water as our primary building material. It's well established that water is found on the subsurface of Mars. In some areas, only a few centimeters beneath the soil, beneath the regolith. And so we selected our site for the habitat in the northern hemisphere in Alba Mons, where we knew that the ice depth was not going to be a substantial barrier. So this is our proposal. We basically proposed a double ice shell with a vertically oriented lander that would provide circulation upwards into various programmatic areas. Double ice shell in particular because we wanted the system to be redundant in case there were asteroids or any sort of like environmental factors that might challenge the integrity of the structure overall. And we were also interested in creating an intermediate zone between the interior and the exterior so that you could, in all likelihood, experience that interior intermediate zone without donning an EVA suit. And we thought that would really add to the quality of life overall for the astronauts. So the design and structure of the habitat. We considered working with regolith for a long time, particularly in light of the fact that ice will sublimate in the environment of Mars. So we saw that as a huge design constraint. So yeah, ice on Mars would be much like dry ice on Earth. But in looking at other typologies, we really wanted to preference a human habitat above the surface as opposed to one buried below. Again, for the reasons I mentioned earlier, why would you travel so far just to be buried underground? And so what we resolved is to basically propose an inflatable membrane and 3D print the ice within the membrane so it's contained and protected from the atmosphere. So here you see, again, some of the development that we went through to resolve on this double ice shell. Some pressure membrane structural analysis to resolve on the overall form. We realized that a more regular structure was going to be something, I guess, more safer, that would have existing precedents in aerospace structures. But we were also invested, just being architects and designers, in creating a sort of beacon on the red planet as a sort of like outpost for the first Martian mission. So this was important to us. So we proposed a clear ETFE membrane with Dyneema reinforcement that would provide additional structural strength as the primary pressure membrane, and the ice would be 3D printed to the inside of that membrane. We proposed 2 airlocks, one for a rover to be attached, and a secondary airlock for EVA missions. We thought it was important that the rover be external to the habitat so that it wouldn't bring in external contaminants. And here we have another view of the access and airlock configuration. And again, this idea of the ice being translucent was incredibly important to us in establishing this outpost as the first human habitat, as a first settlement on Mars. And symbolically, it would add to the quality of life. It would bring value added to the astronauts, but also be a beacon on the red planet for all to see in years to come. And here's another view. So program and experience, I'll go very briefly through the programmatic areas and the experiential aspects of the space in hopes that you might be able to project yourselves and imagine what it would be like to actually be within Mars Icehouse. So you would approach the habitat via the rover and attach to one of the airlocks. On the first level, we have the airlock vestibule, the rover connection, and then the intermediate containment zone that I mentioned earlier, which is not quite inside and not quite outside. And we're imagining that this would be a space where you don't necessarily have to wear an EVA suit, but you could probably get away with just wearing an oxygen mask, for example. So it becomes like almost like a backyard, so that they don't have to be within the lander's floor area all the time. It provides additional flexibility, additional options for how to spend your leisure time. So this is a view of the intermediate front yard where you see the inner core protected by the secondary ice shell. And then on the exterior, this is the IBO, which is one of the 3D printing bots. I'll discuss that in a minute. The second level provides exercise area, medical support, a lab area for working, library, the first of 2 hygiene areas, as well as the beginnings of the greenhouse. So we proposed a vertically oriented greenhouse that would descend from the top of the lander down to the bottom to provide food as well as oxygen for the astronauts. So, and on the third level, we have the second of the 2 hygiene areas, crew quarters for the 4 astronauts, and again, the greenhouse. So here we have a view from the inside of the lander core looking into the crew quarters. And you can see the vertical, we're imagining hydroponic gardens descending from the top of the lander. So here we have the hydroponic greenhouse, again used for food and oxygen for the astronauts. And then on the last floor, we have a wardroom or galley, as well as a food prep area, from which the astronauts can enjoy views of the Martian landscape, again, taking advantage of the fact that the structure itself is materially translucent. So habitat deployment and robotics. This will go through a series of steps that we're imagining for the deployment of the habitat prior to the astronauts' arrival, so that everything is deployed. And we would imagine that simply mining for the water ice, and then 3D printing the water itself would take a number of years. So this would happen well before the astronauts arrive. So the lander would descend. The lander is sized for the SpaceX's Falcon Heavy, or NASA's Space SLS, and we're all well aware of that. The lander would land at the site. Thrusters would blow off the top layer of regolith. The habitat would deploy through the bottom base hatch of the lander. H2O storage would begin and deploy from the lander's reservoir beneath, and this would be an off-site system. The foundation of the structure would be sintered. There you see it sintered. The ETFE membrane would inflate and deploy. This is a precision manufactured membrane done on Earth, created on Earth, and establishing the overall pressure boundary for the habitat. The airlocks would deploy. And then finally, the outer shell of the two shells of the habitat would 3D print. And then the inner shell would 3D print after the outer shell is complete. And an inner layer of hydrophobic aerogel would be provided for installation for the astronauts. Finally, there would be plant growth, and the crew would arrive. So we are proposing 2 robotic assemblies for the sake of 3D printing and mining the water ice from the from below the Martian surface. The Wasibo is a water mining and sintering robot. We don't think this is going to be, we're imagining a series of mini bots such as these to semi-autonomously gather and mine for the water ahead of time, but this would not be, this is not a sufficient system in and of itself. So the Wasibo would capture the water. It would have a bake chamber for creating the foundation, and it basically would use a laser sintering system to create the foundation for the habitat, in addition to extracting or cut the blocks of ice from beneath the surface. So here we have the Wasibo in action. The main distinction that we're creating between this robotic assembly and the IBO, which is going to 3D print the ice on the interior, is that the Wasibo is fully exterior and the IBO fully interior, so that we don't have contamination between the outside and inside of the habitat. So the water is extracted as ice and then melted. The water ice is extracted as a solid and then melted as water, and then the IBO, the ice printing robot, would deposit the water as vapor to the interior of the pressure membrane. So the IBO is an ice printing robot with holding tanks for the material, a printing arm, and a triple nozzle mechanism that would basically deposit the water vapor, silica fibers for structural reinforcement, as you can see here, as well as hydrophobic aerogel to provide to ensure that the habitat is thermally insulated and comfortable for the astronauts overall. And here you see the IBO in action, and the way that it ascends the interior of the pressure membrane is by creating rings or footholds for it to attach onto, and then once it's done creating one full rotation or revolution of printed ring material, it would ascend from those footholds up top and gradually ascend to the top of the structure. So here you can see the displacement and deposition of the material with the IBO ascending, creating footholds for itself to step onto, and then progressively print the next layer of material. And here you can see how the IBO would rotate around, creating those footholds and over time printing the interior of the structure. So ice prototypes and later work. This is the 3D printed model that we created out of resin with a company called Forecast 3D that won at the Maker Faire for the Phase 1 competition, for NASA's Phase 1 competition. And this has been displayed at the Mori Art Museum in Tokyo, as well as a few other institutions. And this is a 3D printed scale ice model that we created in collaboration with McGill University up in Canada. And oh, there we go. So here you see a process video of the scaled model being printed. There is a binding agent that's used as scaffolding material here that when when the entire model is dipped in kerosene, dissolves away. And here you see some additional process photos and some additional process photos. And where this project has gone since then is that we were connected with a research group at NASA Langley to expand on this idea further and propose, and we basically proposed an alternate version of IceHome that did not rely on 3D printing, but that relied on extraction of water and then basically filling a precision membrane, a cellularly crafted precision membrane with water. So it's basically bags of water ice that are then frozen and over time would create the structure. So we've been working with them to come up with the systems architecture and develop a concept of operations for how this structure might be developed. And we're in the process of creating a subscale demo for water extraction and filling of ice bags, which we're using Teflon at the moment, to basically freeze and conduct tests on. So that's where the project has taken us. And for more information, please visit marsicehouse.com or spacexarc.com, which is my organization. And I think we have time for questions. So that's that.
How does the temperature inside the growing plants, how does that work because of the ice involved?
We were imagining, that's a great question. We were imagining that the redundancy between the inner ice shell and then the outer ice shell would provide enough thermal insulation for the plants to be happy. And we're also imagining that the mechanical systems, the ECLIS system, as well as the systems that are embedded within the lander core are going to provide an environment that's going to be okay for the plants to be sustainable. And then the hydrophobic aerogel insulation layer is the other thing that keeps things insulated from the inside to the outside.
So there's the insulation layer on the inside of the ice?
Exactly. Everything works from the outside in, yes. So you have the precision manufactured membrane, and then the ice, and then the aerogel.
Yeah, I love this idea, and I always like to check out those ice hotels they build in Sweden and in Canada every year. Have you been to those?
Yeah, I haven't been, but I'm familiar with them, yeah.
But those are kind of block structures, and ice is kind of like concrete. With compression, you can actually make arches and all kinds of crazy stuff.
Right.
They used to use it for construction. I'm probably you've seen this in northern Canada and Alaska, right? So my idea had been just to put a pole up and just it had a sprinkler head on, just went around and made a huge dome, and then hollow it out. And also I thought, well, if you did it over a canyon, you'd have all this huge 3D space below you. If you could figure out a way to arch it over a canyon, then you'd have all this area already pre-mined and already pre-excavated, so you wouldn't have to like create a huge above ground space. And you just cover it with a dome and you're done. But also I like the idea of like self-healing to be able, because this is gonna, like you said, sublimate, you're gonna lose material, or also just put a coating over it, to kind of keep that from happening. But anyway, I love the idea, and great presentation.
Thanks. We definitely considered a gantry system for 3D printing the ice from above, but we were concerned about the deployment of that system ahead of time. And what we continued to realize were that mini-bots not only introduce redundancy to the system if the gantry system were to fail, but I'm glad that didn't happen earlier. Yeah, but it's a great point that you raised. Thank you. Yes. So we are introducing a material called aerogel that's basically going to insulate the inside from the outside to make sure that the ice isn't cold to the touch, so that the astronauts, when they're in their crew quarters, for example, are going to be protected by this layer of aerogel material. Yes, please.
So how'd you do the windows? Because that didn't seem like translucent, so that seemed transparent. When we bring it in glass, and if it's all made out of kind of ice, you would get sort of a blue light on the inside. Did you look at all how that would affect the astronauts' vision when they head out into a very red light environment?
That's a great question. So those windows, we were definitely not imagining that they would be glass, but we have been working with an ice researcher over at Brown as well as at JPL, and we've been looking into sort of anticipating what the conditions are going to be so that we can produce the correct grain size to achieve the translucency that we want. So we've been, in the experiments that we've been doing with NASA Langley, we've been looking into how to basically recreate the microcrystalline structure of ice so that it can accomplish the translucency that we want. We're not 100% there yet, and quite frankly, we're not sure that ETFE as a material, as a membrane, pressure membrane is going to be sufficient for radiation protection itself. So there's still lots of questions, there's no doubt, and I think ice translucency is definitely one of them.
Related to that, so do you have any plans for keeping the dust from obscuring the ice after the fact?
That's a really good question too. No, we haven't really thought about that, but I think depending on the sort of like viscosity of ETFE and how it's coated, I would imagine that no matter what it is, it's going to be a multi-composite material and it's going to have lots of coatings. That might be something that we can look into later on. Yes, please.
You have the rover outside to prevent contamination, but you don't have the astronauts take their suits off outside to prevent contamination. Won't they bring it in with their suits just like the rover would?
We're imagining that within the airlock, they would take their EVA suits off before coming in. We weren't imagining that they would fully walk in with their EVA suits. So that's another reason for the intermediate containment zone, the inner outer yard. It becomes a sort of barrier, a buffer area between the habitation areas, which are fully enclosed within the lander core, and this becomes a sort of mediated area between inside and outside. But we weren't imagining the EVA suits would be there, no.
Well, I live in New Mexico, and I can tell you that the dust comes with you.
Fair enough.
I think we have time for one more question.
Okay, please.
I'm not sure I understand how all the layers are produced. I understand the ice is 3D printed on the inside of the membrane. Right?
Yes.
So you deploy the membrane and plate it, the robot goes around on the inside depositing ice on the inside.
Yes.
And you've got the layer of aerogel. How is that applied?
The aerogel would also be sprayed on to the ice afterwards. So it's a three-step process. First, the pressure membrane is inflated, the habitat is pressurized, then the ice is printed, and then the aerogel is deposited. It would be a very, very thin layer, and aerogel is also a very brittle material. So how that happens is something that we still need to look into, and there's a good amount of material science research involved in all of these sort of like propositions that is just going to have to take some time and we'll look into.
Are you planning a full-scale prototype someplace?
A full-scale prototype, no, but like I said, we're developing a subscale demo of a variation of this project called Mars Ice Home, and that's just going to be with pre-inflated bags of Teflon that are then filled with water ice, and that will be the first step forward in this project. Anything else?
Very much.